Okay, so in the last lecture we saw that a Thevenin equivalent or any network can have a Thevenin equivalent, and that is represented by a Thevenin equivalent circuit. And what that Thevenin equivalent circuit is, that consists of an independent voltage source connected with a resistance, or you can call that as a practical source. So that is what it basically said, that if you have a network, it can be converted, or it can be shown as a practical source, or here to be more precise, practical voltage source. That is what the Thevenin equivalent is, and the value of that source, or that source part, will have a VTH, called VTH, and the resistance part is an equivalent resistance. And we also saw how to calculate that particular source voltage, okay, by considering the voltage by calculating the voltage across the terminals of interest. And similarly, the resistance can also be calculated by considering the terminals of interest with all the independent sources zeroed out. Okay, now based on that same Thevenin equivalent, there is another possibility. Okay, what is that possibility? If you have a current source, a practical voltage source, okay, a practical voltage source, then it can always be converted into practical current source. That is what we have already seen. So if you have got a Thevenin equivalent, then you also can represent it by its dual form, okay, or a current equivalent form, and that current equivalent form is called Norton equivalent. It is due to another person who tried to get that dual equivalence of that Thevenin form. Okay, so if you have a Thevenin form, you can always get its dual as a Norton form. In certain cases, it may not be possible to have Thevenin form, and you may get only Norton form, or it may have only Norton form and not the Thevenin form. That is the case when somehow the resistances try to, or becomes equal to 0, or becomes equal to infinite. So in those cases, one of the forms do not exist. Okay, so that is a special case. But in all the cases, if you have a Thevenin equivalent, then you also have its equivalent, Norton equivalent. Okay, so now here finding Norton equivalent and Thevenin equivalent are quite similar. Here if you see, this is what we considered next time. This is last time, that this is a complicated network for which we want to have that equivalent. Okay, so this is the equivalent Norton circuit. Okay, R equivalent and I Norton. So this is called IN and R equivalent. So for this, across this particular, you have to always be clear about the set of terminals. So for this particular terminals of interest A and B, we want a Norton equivalent for this particular complicated circuit. And to get that Norton equivalent, first we'll have to find what is the current flowing into it when the terminals of interest, that is A and B, are shorted out. Okay, when you short it out, this becomes a short circuit and there is a current flowing into it, and that itself is a current, or a Norton equivalent current, IN. Okay, in the same conditions you found the voltage equivalent, but here you didn't, for finding a voltage equivalent you don't short, obviously, because that becomes a 0 voltage. But the condition was same. There you wanted to find out voltage, and you kept A and B and found the voltage across here, across that particular A and B. Here you are interested in Norton equivalent current, so you short A and B, and find out the Norton equivalent. This itself is equivalent current source, and the R equivalent is found exactly the same way we did for Thevenin. That's why it is not called Norton equivalent or Thevenin equivalent resistance, simply R equivalent. Okay, so it is same resistance which you did for Thevenin equivalent. And how did you find it? These are the terminals A and B. You remove all the independent sources from it. Removal of all the independent sources means all the independent voltage sources are zeroed out by shorting their terminals. all the current sources are zeroed out by opening their terminals. Dependent sources are kept as it is. That is simple formula, and that is how you find R equivalent, and that is true for Thevenin as well as Norton equivalent, both cases. And this is the equivalent representation across terminal A, B, the current form representation, that is called Norton equivalent representation. Now let us take the this I have already Thevenin equivalent, and okay, we'll find Thevenin equivalent here for the same circuit. Sorry, not Thevenin. We find Norton equivalent for the same circuit what we did in the earlier lecture. Okay, so this Norton equivalent, like Thevenin equivalent, it is same circuit, and we will find go according to the rules which we have just said. That is, you first we are interested in A and B, so we first short circuit A and B and find how much is IN. And when you short circuit this terminals A and B, obviously Vx becomes 0, and this actually goes out of picture, or it becomes 0 because Vx is 0. So this current flowing in through this is 0, and current flowing through this is 0 means it is open circuit across these two. So this is what you get, and you can now calculate the value of IN, and value of IN is basically 4 upon 5k. This 2 come straight away in a very simple manner. So in this case, Norton equivalent, finding Norton equivalent is quite easy compared to Thevenin equivalent, where you wrote the equation and found Vx. But of course that can happen. So here it is IN, that is 4 by 5k. Now we are going to find out how much is the equivalent resistance. Okay, so equivalent resistance, again we are going with the same concept. Okay, here I have explicitly shown that this is shorted out. Okay, so effectively 4 volt is not there, it is basically this which is important. Okay, just to show that here I have done it. In earlier circuit 4 volt was not there, that's all. That is removed, and that is shorted. And you can write those equations again over here and find again V by I. Here I have explicitly said 1 volt is being put here, and I'll try to find value of I, and this Vx, or this 1 volt itself is Vx. Okay, so this is 1 volt, and when you put into this equations, you can just see here equation I have written for the same node equation which we did last time. Okay, you can just check, same equation is there. Of course I have already put the value of Vx equal to 1, so here also it is 1, and by that way you can find the value of I, which comes again same, and R is equal to 1 by I, which comes out to be 10 raised to power 4. So it is same equivalent circuit, and now I have a Norton equivalent having this as 4 by 5k, or you can say 4 by 5 milliamperes, and of course this is same as what we had in this and the earlier Thevenin equivalent, that is 10 kilo ohm, I suppose, that is k ohm. And if you match this to the Thevenin equivalent, let me find Thevenin equivalent from here itself. The voltage source, equivalent voltage source, that is by source conversion, the voltage source would be 4 by 5 into 10k. 4 by 5k into 10k would be the voltage source VTH, and how much it comes out? It comes out to be 4 by 5, so it is same 8 volts, which you, if you remember in the last lecture, it is 8 volt was VTH, and of course this remains the same, that is 10 kilo ohm, and this is the Thevenin equivalent, and this is not an equivalent. You could have calculated directly from the Thevenin equivalent which you did in the last class, it's not an equivalent, or if you have calculated not an equivalent, you can always find Thevenin equivalent. In very specific cases you may not be able to find interchange Norton equivalent into Thevenin equivalent. For example, if I say that if I have a Norton equivalent something like this. That means a open circuit. This means a open circuit. And now if you want to find Thevenin equivalent, now you cannot do it, okay? Or other way around, if you have this as a Thevenin equivalent, resistance comes out to be 0, then also you cannot find Norton equivalent because it becomes undefined. So undefined doesn't mean that you can put it 0 or infinite, okay? So that is why this will in that cases, specific cases, it may not work. So a network sometimes may have only its Thevenin equivalent or a Norton equivalent. One important interesting fact which you will find here is, if you have a Norton equivalent, if you see IN is 4 by 5K and VTH is 8 volts, and if I find VTH by IN, okay, so VTH is 8 upon 4 by 5, 8 upon 4 by 5, so 4 by 5 means how much? 0.2? 5 eighths, sorry, 5 eighths, so 8.8 is it? Or you can write 4 by 5 here, and it comes out to be 10 kilowatt. So sometimes it may be easier to find IN and VTH in certain cases and then get the R equivalent. All three are related. So that is an interesting point. So if it is difficult to find VTH, you can VTH. If it difficult to find R equivalent, and if it is easier sometimes to find IN and VTH, then you can find IN and VTH and then derive RTH from that. Okay, so one more I think okay, I'll just stop here for a while so that the video is small, and then I'll come in the next video. Okay, thank you.